Good day, my name is Tully Spanda. Welcome back to another presentation on Fluid Mechanics 101, Complex Piping Systems. So far we've discussed straight length of pipe with valves and fittings. Complex pipe systems include pipes of different diameters in series and parallel configuration. In industry, you find that there's really one pipe of the same diameter connecting to equipments. You find that there are different pipes of different pipe sizes within a system. Series piping in its simplest form consists of two or more different pipe sizes connected end to end as illustrated in the figure below. As you can see, these three pipes are connected together, but they're of different sizes. You can find sometimes you use reducers, sometimes there are certain construction or certain divergences, or there are flanges, or they are welded together. Pressure drop calculation in series piping may be handled in one of the two ways. The first approach will be to calculate the pressure drop in each pipe size and add them together to obtain the total pressure drop. So it means we calculate the pressure drop from here to there, from here to there, from here to there, and also include these certain contractions or certain enlargements, but it becomes a complex calculation. It's tedious. Another approach is to consider one of the pipe diameters as the base size and convert other pipe sizes into equivalent lengths of the base pipe size. So the calculation becomes less complex or simple. The resultant equivalent lengths are added together to form one long piece of pipe of constant diameter equal to the base diameter selected. Then you use this equivalent length to calculate your pressure drop using either the Hazel-Williams equations or the Darcy's equations. The pressure drop can now be calculated for a single diameter pipeline. All valves and fittings will also be converted to their respective equivalent pipe lengths using the LD ratios, and I'll give you an example of this. You see what I'm talking about. Consider three sections of pipe joined together in series using subscripts 1, 2, and 3 and denoting the pipe length as L, inside diameter as D, flow rate as Q, and velocity as V. We can calculate the equivalent length of each pipe section in terms of a base diameter. This base diameter will be selected as the diameter of the pipe section D1, which means the first section of your pipe. You take it as your base diameter. Since equivalent length is based on the same pressure drop in the equivalent pipe as the original pipe diameter, we will calculate the equivalent length of section 2 by finding that length of diameter D1 that will match the pressure drop in length L2 of diameter D2. I hope that makes sense, which means we want the length, which is the equivalent length, which is of the similar size of your base diameter D1 that will have the same pressure drop as the equivalent length. I hope it makes sense, but as you're doing the calculations, they need to make sense. So using the Darcy's equation and converting velocities in terms of flow rate, we can write, if you remember, we go back to the Darcy's equation. So which means if I were to put here is L equivalent D2, right? Put that is equal to F, which is my L1, D1 here, which is my base, my base diameter. Since we said the head loss should be equal, right? Then if you cancel out, then you simplify, you get that L equivalent D1 to the power 5 is equal to L2 D2 to the power 5. Of course, this comes from here. You get D squared, you put then simplify, you see that it will simplify to D to the power 5. Therefore, the equivalent length of section 2 based on diameter D1 is equal to LE is equal to L2 D1 over D2 to the power 5. Similarly, the equivalent length of section 3 based on diameter D1 is LE L3 D1 over D3 to the power of 5. The total equivalent length of all three pipe sections based on diameter D1 is therefore L total equals to L1 plus L2 D1 over D2 to the power of 5 plus L3 D1 D3 to the power of 5. The total pressure drop in the three sections of pipe can now be calculated based on a single pipe of diameter D1 and length LT. Example: 3 pipes with 14-inch, 16 and 18-inch diameters respectively are connected in series with pipe reducers, fittings and valves as follows. 14-inch pipeline, 0.25-inch wall thickness, 2,000 feet long. 16-inch pipeline, 0.375-inch wall thickness, 3,000 feet long. 18-inch pipeline, 0.375-inch wall thickness, 5,000 feet long. 1 16 by 14-inch reducer, 1 18 by 16-inch reducer, 2 14-inch 90 degrees elbows, 4 16-inch 90 degrees elbows, 6 18-inch 90 degrees elbows, 1 14-inch gate valve, 1 16-inch ball valve, 1 18-inch gate valve. Using the Hazel-Williams equations with the C factor of 140 to calculate the total pressure drop in the series water piping system at flow rate of 3,500 gallons per minute. Flow starts in a 14-inch piping and ends in the 18-inch piping, which means the 16-inch is in the middle. Since we are going to be using the Hazel-Williams equations, the pipe in series analysis will be based on the pressure loss being inversely proportional to D to the power of 487 instead of 5 when using the Darcy's equation. So you should take note of that. You also change if you're using the Manning equation, where D is the inside diameter of 5 per volume equation. Take note, this is the inside diameter, not the outside diameter. So here's the Hazel-Williams equation: 4.73 multiplied by length over Q, which is your volumetric flow rate, over C, a factor which we are given to the power of 1.852 or over inside diameter to the power of 0.487. We will first calculate the total equivalent lengths of all 14-inch pipe fittings involved in terms of the 14-inch diameter. So it's a straight pipe, 14-inch, 2,000 feet. So which means, of course, this one doesn't change because it's the base diameter. 2 14-inch 90 degrees elbows using the LD ratio of 30, and these two of them dividing by 12. Of course, to convert from inches to feet, you get 70 feet of 14-inch pipe. Same applies to one 18-inch gate valve. The LD ratio is 8. You get 9.33 feet of 14-inch pipe. Therefore, the total equivalent of 14-inch pipe, its fittings and its valves, you get is 2,079.33 feet of 14-inch pipe. Similarly, we get the total equivalent length of 16-inch pipe, fittings and valves as follows. Straight pipe, 16-inch, 3,000 feet is equals to 3,000 feet of 16-inch pipe. 4 16-inch 90 degrees elbows. We convert again using the LD ratios of 30 divided by 12 to convert from inches to feet. We get this 160 feet of 16-inch pipe. 1 16-inch ball valve. Same applies. We convert, you get 4 feet of 16-inch pipe. Therefore, the total equivalent length of 16-inch pipe fittings in this valve is 3,164 feet of 16-inch pipe. Finally, we calculate the total equivalent length of 18-inch pipe fittings and valves as follows. Straight pipe, 18-inch, 5,000 feet is 5,000 feet of 18 feet. 6 18-inch 90 degrees elbows. The LD ratio is 30. We get 207 feet of 18-inch pipe. 1 18-inch gate valve. So its LD ratio is 8. You get 12 feet of 18-inch pipe. Therefore, the total equivalent length of 18-inch pipe fittings and valves is 5,282 feet of 18-inch pipe. Next, we convert all of the preceding pipe lengths to the equivalent length, equivalent for the inch pipe, based on the fact that the pressure loss is inversely proportional to D to the power of 4.87, where D is the inside diameter of pipe. So now the 2079.33 feet of 14-inch pipe doesn't change, of course, remains like that. Then the 3,164 feet of 16-inch pipe, we convert. Remember, we say D1 was the inside diameter is 3.5, so the 16-inch, the inside diameter is 50.5 to the power of that, so it's equivalent to 1,740 feet of 14-inch pipe. Same applies to the 18-inch pipe, right? It's equivalent to this one. It's 5282, but we want to convert this to the equivalent of 14-inch pipe, so we divide by 13.5 all over 70.25 to the power, so it's equivalent to 1,601 feet of 14-inch pipe. Therefore, adding all the preceding lengths, so we get total equivalent length in terms of 14-inch pipe. It's 5,429 feet, 429 feet of 14-inch pipe. So remember, now we have to account for reducers. We did account for valves, but not for the valves and the elbows, but not for the reducers. We still have to account for the 16 by 14-inch and 18 by 16-inch reducers. The reducers can be considered as certain enlargements for the approximate calculation of the head loss using the K factor and velocity head method. For certain enlargements, the resistance coefficient K is found from K is equal to 1 D1 D2 squared all squared, where D1 is the smaller diameter and D2 is the larger diameter. Right, D1 is the smaller diameter, D2 is the larger diameter. So for a 16 to 14-inch reducer, we use the smaller diameter, 13.5 inside diameter. And inside diameter of the larger one is that squared. You get it 0.0468. For 18 to 16, same applies. So 1 minus 15.25, 70.25 squared, all squared. You get it 0.047. The head loss through the reducers will then be calculated based on K, E squared over T, 2G, which is your velocity. Remember, this velocity is for the smaller pipe, D1. Flow velocities in the 3 different pipe sizes at 3.5 gal per minute will be calculated as follows. So I want to convert the 3.5 gal per minute to cubic feet per second. You get it 7.798. You can do the calculation or just go to Google and do that. So the 18.5 inch is equals to 1.125. It's supposed to be feet here, my mistake. Therefore, velocity in 14-inch pipe is equals to Q over A, which is your volumetric flow rate over cross-sectional area, which is same as pi r squared or pi t squared over 4. And substituting, remember we converted our volumetric flow rate to that 7.798 cubic feet per second divided by pi by our diameter, inside diameter in feet, which is 1.125 feet squared divided by 4, we get that the velocity is 7.85 feet per second. Then for the 16-inch pipe, we do the same thing. We substitute here, D is 1.22, we converted that 15.25 inside diameter to feet. We get it 6.15 feet per second. Same applies for the 18-inch, converted that to inside diameter in feet. Sorry, I kept putting inch, but it's in feet actually. Put that in feet, you get is 4.81 feet per second. So the head loss now through the 16-14-inch reducer is equals, remember the K factor is that volume and volumetric velocity on the smaller pipe is 7.85 squared over 2G, G, which is your acceleration due to gravity, is 32.2, then 2 of it is 64.4, you get that. Same applies for the 18 to 16, we get 0.028. You see these head losses now, it's minor, so that's why you call them minor head losses, I explained on the previous presentation. So these head losses are insignificant and hence can be neglected in comparison with the head losses in straight length of pipe. Therefore, the total head loss in the entire piping system will be based on the total equivalent length of 5429, since this one they just minor, it's less than 150 or 14-inch pipe. Using the Hazel-Williams equations, the pressure drop at 3,500 gallons per minute is that. Remember, I showed you the Hazel-Williams equation. Let's go back to it again here. Okay. This is the Hazel-Williams equations. If you remember, head loss when using the Hazel-Williams equation. Let's go back there. But this one is based on 1,000 feet of a pipe. So I think I showed you this version of the Hazel-Williams equations in the previous presentations. So this 140 is just a factor. This is that 3.5 gal per minute, and this is just 1 over. Remember, we're using the 14-inch diameter, so but the inside diameter is that. So if you go to the previous presentation, you'll see this form of Hazel-Williams equation. Therefore, we found it for 1,000 feet, our head loss is 12.7 feet. Therefore, now we want, what is it for now? 5,000 feet. We use this equation 12.7 by 5,429 divided by 1,000. We get that for 5,000 feet, it's almost 68.95 feet, which is same as 29.85 psi. Of course, the ratio now, this is 4,000, this is 5,000, it's almost 5 times. So if you say 12.7 by 5, you get this. That's the math there. Once again, thank you for watching. And if you have any questions, queries, additions, don't hesitate to contact me on my email address towaspand@gmail.com. Like, comment, and subscribe to my YouTube channel to learn more lead engineering stuff. And as I said, the form of the Hazel-Williams equation I used to calculate for my final solution is different from the one which is presented from above, but it's the same as the one on my previous presentation. So you can just go back and refer to it. And thank you so much once again. See you on the next presentation. Ciao, ciao.